Okay, so let's now consider a different current distribution. And so in order to create a situation that has symmetry that we can appeal to, let's again invoke an infinitely large plane. So this is an infinitely large plane, which means it goes off in all of these directions. So what I've drawn is a section of the plane, but that's the plane, and it has current flowing in that direction. So here's the current density, and we basically can think of this as an infinite collection of infinitely long current carrying wires, and we have a current density, I don't know, let's call it lambda. So that's the magnitude of the density, and the current is flowing in that direction. So if we look at this sort of in the plane, so here we are looking at the current coming straight at us, we would see the plane like that, and the current. So if we make red arrows representing the current, then it would be equivalent to infinitely long wires of current. So it's a collection of magnetic fields that we're familiar with, and it would look something like that, and we would continue on that way. So if we want to find this magnetic field, the last thing that we really want to do is to appeal to a brute force approach, which would require that we integrate this kind of thing. Right? We don't want to think of this kind of thing. Where we could think of this as infinitely long lines, and we could integrate from negative infinity there to positive infinity there, and then from negative infinity there to positive infinity to the right. That would be a very complicated calculation to set up. So it would be easier to take advantage of symmetry and to appeal to Ampere's law to get the magnitude of the magnetic field. And then, given the distribution of current, figure out what the direction of the field must be. So if we look at things from this perspective, then it's clear that the magnetic field at this point here, at some height above the plane, must have the same magnitude as the magnetic field at that same height, but at some distance further down. And the direction of the field must also be the same there, because the current distribution that both of these points see is the same. And the same goes for all points at that same distance. So I can include that as part of a line. So we are at some distance here. Let's say we are at a distance from the plane D. And so it would be true that the field there has the same magnitude as it does a distance d below the plane. So even here we are at a distance d. And so these two lines have the same magnetic field and magnitude, but different direction. Okay, we can figure out that direction by appealing to the part that gives us the direction of the magnetic field from the current distribution. And so all of the current elements are coming straight at us. So the index finger is pointing directly at us, and the middle finger will tell us the field direction at different points. So we can identify that the field above must be to the left and the field below must be to the right. But another way of thinking about this is that the net magnetic field is just the combination of magnetic fields that are the magnetic field of the infinite long current carrying wire. So the magnetic field of the infinite long current carrying wire circles around, and so when we start to add more of these, right, we want to respect the basic principle that says magnetic fields curl around the source, but if the source is now sort of stretching out this way, then the magnetic field has to do something like that and stretch out. So we'll make some blue magnetic field lines. Right, the magnetic field has to do something like that and stretch out, and eventually, if we stretch this out enough, we are basically making a field that above, let's see if I can use a different color here, green here, above is basically getting more and more horizontal. Right, the longer this is, the more the field above becomes horizontal, and the same for the field below. And eventually, if we go to infinity in both directions, the field is perfectly horizontal above and perfectly horizontal below, and in some sense comes around at infinity. So at any finite distance, we have a perfectly horizontal field. It's this ideal configuration of current, which we can't really generate in practice. So Ampere's law, so we want to close this path off because we need a closed path. That should be a straight line. And if we look at it from this perspective, it basically says that we are going to do something like this, above and below. And that's our closed path. And when we integrate, let's draw some more field lines. So we have green field lines on the above path, but what about the field lines on this side? Well, here we might imagine that the field is a little bit stronger because we're closer to the current, but it has to be to the left, whereas here it has to be to the right. So if we're at the same distance below as we are above here, then I'm going to try to make the field line a little bit larger, but same as larger than here and here, but same length as there. And the same is true here and here. It's just that way, but the magnitude is the same as here, here, and here. So let's choose a direction for the path. And so maybe this is the direction we want to integrate in. That's dl. Here's another dl here. Here we're going this way. Right, we're integrating counterclockwise. We can see that we'll get 0 here on this side because B, right, the magnetic field B is in green here, and it's 90 degrees from the DLs, so the dot product here gives us 0. The DL here is this way, so it's, oops, sorry, I'm trying to make them in blue. So the DLs and the magnetic field on the top and bottom side are aligned. Right, see that? DL and B are aligned here, and here they are at 90 degrees, so we get no contribution from the sides, very similar to the application of Gauss's law to electric fields for the infinitely large, uniformly charged plane. Except there, of course, we had to use surfaces as opposed to paths or lines, closed surfaces as opposed to closed paths. But you'll see similar things. The sides don't contribute, and so what does the calculation reduce to? On the top side, we get whatever the magnitude of the magnetic field is, B times that length, and we choose that length. So let's say we choose a length L. So it's B times L. We get nothing on the side here. Here, again, we get whatever that B is, B times L, and nothing on this side. So the left-hand side of this expression reduces to 2B times L, and the right-hand side is mu naught times the current that's inside that goes through this area that has our closed loop as a boundary. And so we can see that here is all the current. Well, how much is that? Well, it's the density times the length. So we call the density lambda, so we get lambda times this length, which is, again, L. And that's what Ampere's law looks like, left-hand side and the right-hand side. And so here we get 2, the magnitude of the magnetic field times the length equals mu naught lambda times L. Very similar to Gauss's law for electric fields for the infinitely large uniformly charged plane, where we had twice the electric field times the area. Right there we had a top area and a bottom area, and the left-hand side became 2E times area, and the right-hand side was charge density times one factor of area. Here it's just the length version of that, because magnetic fields circle around the source and they don't diverge away. And so we get the magnitude of the magnetic field is mu naught lambda over 2, and the direction is such that above it's to the left and below it's to the right.